Hello and welcome to BioRules video lessons. Today we are going to be talking about two nutrient cycles, nitrogen and potassium. So let's first talk about nitrogen. Nitrogen is an element very abundant in our planet. 78% of our atmosphere is nitrogen gas. It's the most abundant gas in our atmosphere. Hey, so that's good. Now we have it all around us. Every time we inhale, we get 78% of nitrogen. Not so quickly. Plants or animals don't manage to get nitrogen gas into their bodies to transform into biochemical nutrients. And that's a shame, because plants and animals, they need biochemical nitrogen in the form of amino acids, like with what you have here, or in the form of nucleic acids and a few other forms. So nitrogen is all around us. Plants and animals, they need it, but they don't manage to get it. So what are we going to be doing? Good thing is that there are two groups of bacteria. One is called Rhizobium, which is a mutualistic bacteria that live in some nodules in roots of some plants, like this here, and Azotobacter, which is a free-living bacteria in the soil that are capable of transforming N2 from the atmosphere into ammonium, or ammonia, a chemical that then can be transformed in the soil to be used by plants. Hey, very good. So how is this thing going to be working? Let's show you then the nitrogen cycle. This will be easier. Nitrogen gas in the atmosphere. There we have free-living Azotobacter. So that's one of the bacteria that's going to be transforming nitrogen gas into ammonia, a compound that can be used. Mutualistic Rhizobium. And also there's a third way, which is lightning, that produces a little bit of ammonia, and industrial ammonia. So we can actually in our industries, we can spend a fair amount of energy to transform nitrogen gas into ammonia. So there are ways for you to be doing this. In the living systems, we depend on the Rhizobium and Azotobacter. What do? They transform nitrogen gas into ammonia, NH3. This nitrogen, in the way of ammonia, still cannot be used by plants or animals to put into their body. So this here needs to be transformed by a nitrifying bacteria that's going to be transforming ammonia into nitrates, NO2-. And nitrates still cannot be used. So there's another group of bacteria called nitrifying bacteria that are going to be transforming nitrates into nitrates. Oh, nitrates, NO3-. This is the nitrogen that can be taken by plants. So plants are going to be absorbing nitrates and transforming that into plant protein or other chemicals like nucleic acids. And then the animals eat plants and they get protein and other biochemical nitrogen to put into their bodies. That's the way that we do things. When animals die or plants die, or when they excrete, for example by urination, they release nitrogen compounds to put the excess nitrogen out of the body. Now, we humans, we put most of our nitrogen out by urea. Some animals put ammonia, some animals put uric acid. But no matter what, these chemicals that are put out by animals in excretion or by dead plants, dead animals, dead anything, goes through a process of ammonification, becomes ammonia again, and gets in the cycle back again to become nitrates and then nitrates to be used again by plants. This, however, there is another bacteria here, this is quite important, that causes denitrification. We'll see the names of these bacteria in a while. This bacteria is capable of transforming nitrates, that is useful for plants, into nitrogen gas. So basically that bacteria over there kidnaps nitrogen that could be useful by plants and throw it away back into nitrogen gas. And then nitrogen gets a certain equilibrium. Let me show you here a cycle. The most important ones for you to remember the name is Rhizobium and Azotobacter. Those are two bacteria that transform nitrogen gas into ammonia. There's another group of bacteria that's over there, Pseudomonas denitrificans. This name is fairly important because this is the one that steals nitrates from the soil and throw it back into the atmosphere. And there's a third group of bacteria, the Nitrobacter, transforms nitrates into nitrates, and the Nitrosomonas that transforms the ammonia into nitrates. Those are not very important. I've seen In some exams they're asking about those guys there, but they're not the most important ones. The most important ones here are those two, followed by in a distant place by the robber Pseudomonas denitrificans. Okay, so here we have another diagram showing the nitrogen cycle, where we have now the nitrogen fixing bacteria transforming nitrogen into ammonia into the legume roots. This is the rhizobiums. Here, the free living ones that transform into ammonia in the soil, the azotobacter. These guys here, they make ammonia, so then you have the nitrification that makes nitrates, then you have another nitrifying bacteria that makes nitrates, and the nitrates that can be assimilated by plants, that can transfer to the animals, that can throw it back in when they urinate or when they die, into the soil. Decompose can also use it and put it back over there. Okay, and there is the Pseudomonas that transforms nitrates back into nitrogen gas over there. In this cycle, we didn't put the way that lightnings and industrialization are capable of doing this. So this here will be lightning and industries that can do this kind of stuff here. Okay, so another diagram here of the nitrogen cycle for you, if you think that you need another way of looking at this here. So this is the nitrogen cycle, quite important for us. And one thing that we think, okay, we produce plants. No, the plants grow, corn, soybeans, whatever, no, carrots, beetroots. The plants grow over there. And then the farmer gets these crops, they take it away to the cities, and we eat. And then we take whatever we need, but the compost, the excretion, the feces, never go back to the field. So that's a problem, because the soil is continuously depleted from nitrogen that's taken away when the farmer sells the products, and then we don't put it back with our compost. At least we don't put much back with our compost. Luckily, the soil has bacteria that are capable of making ammonia to then be made into nitrates. And some plants, especially legume plants, from the family of the beans, the soybeans, and on, those plants, they have lots of rhizobiums associated with them. So crops rotation is a very smart solution for losing nitrogen from the soil when we have crops. Basically, what farmers do is to plant something that's going to be getting nitrogen from the air, like legumes, soybeans, for example, or beans, or something like that, and it's going to be getting rhizobiums that will get nitrogen from the air, put it in there, used by these plants, but usually there's an accident. And then the next time we plant something that's going to be using that nitrogen, then we put something that's going to be using that nitrogen, the nitrogen reduces, and then you rotate again for something that's going to be putting nitrogen into the system back again. So this is the idea of making crops rotation. Okay, legumes, and then you alternate with something else that consumes lots of nitrogen, and then you go back to the legumes that's going to be getting nitrogen with the rhizobiums into the soil. Okay, one important thing for us to pay attention with nitrogen especially is that some situations favor the development of Pseudomonas. So Pseudomonas here loves waterlogged areas. So basically areas that get submerged with no still water over there. Oxygen drops, and then these bacteria, they love it, and they grow, and then you have lots of Pseudomonas stealing nitrogen from the soil. A result is that the soil gets poor in nitrogen. So if you don't want the soil to become poor, it's good to avoid waterlogging. Some areas are naturally waterlogged, some areas naturally have low nitrogen in the soil. Plants have evolved to solve that problem by becoming carnivores. Carnivore plants are plants that eat animals. Why? Do they need the energy? No, they do photosynthesis, they don't need the energy. But they do need nitrogen or maybe even some other chemicals. When these plants eat the animals, they absorb nitrogen-rich chemicals and they put into their bodies because the soil where they live don't have much nitrogen. So carnivore plants are there eating animals to be able to get the nitrogen, maybe a little bit of phosphate and other stuff as well, but nitrogen is an important thing for carnivore plants, and they get by killing animals. Okay? Another cycle that's quite important for the plants is the phosphorus cycle. Phosphorus cycle is a little bit more tricky than the nitrogen cycle, because the nitrogen cycle, we have plants that are capable, not plants, we have bacteria that are capable of getting nitrogen from the air and put into the soil, and then the plants manage to get the nitrates from the soil and put into their body. So there is a cycle there. So the nitrogen is usually replenished in the soil if you don't overexploit it. But phosphorus is a different game. There is no phosphorus in the atmosphere. Phosphorus comes from rocks. So when you have phosphate rocks, like these ones here, when they suffer weathering, the soil receives phosphate. But this is a very slow process. So there is phosphate in the soil from weathering, from erosion of rocks. The problem is that the phosphate is assimilated by plants, and the plants then are eaten by animals, or they are taken away to the cities for us to eat. And then the leftover, the excretion, the excrement, the feces of the animals, the leftover from food, usually we don't put it much back to go back to the soil. What happens is that there is a big runoff that leaches to the water bodies, to rivers and then to the ocean. So usually there is a continuous runaway of phosphorus, phosphates, into water bodies. So as a result, the soil is continuously getting impoverished. In a natural environment, these things, they end up balancing each other. But nowadays, with heavy, massive agriculture to feed all human beings in the planet, we are using much more phosphates from the soil than we are putting back by the composting. So as a result, the phosphate ends up in water. They are used by the water plants, they are used by the animals, and they keep cycling over there. A little bit goes back with some fish that are eaten by animals that end up leaving the excess beside the rivers. So this is an example of bears. Bear territory usually have a lot of phosphorus, lots of phosphate, because the salmons, they get into the rivers bringing phosphorus from the ocean, and the bears, they eat part of the fish, but they don't eat everything. They poo over there and the phosphorus go back. But the problem is that this cycle here in the water, it happens, but it doesn't come back very often to land. Most of it end up getting sedimented and making new phosphate rocks that will be uplifted, and then will become phosphate rocks to be eroded again and go on the cycle. But the problem is that this here takes millions of years to happen. So this cycle is not fast. And in the way that we are consuming plants in agriculture, this here is not going to happen fast enough. So as a result, we have to explode rocks to be able to grain them and to get fertilizer phosphate. The problem is that the fertilizer phosphate used in agriculture is very efficient. We can produce our foods, but the problem is that we are running out of rocks containing phosphate. So this here is the consumption in metric tons times a million. Times 10 to the power of 6, a very big number. This is the consumption that went up massively after World War I and reached numbers very, very, very high here by the end of the 20th century. And the problem is that if we keep using in this level, we are going to be running out of phosphates in something between 50 to 100 years to use as fertilizer. So, or we find ways to optimize the leftovers of our food, to do more composting, to process the sewage with our feces, to be putting back into nature, or we will need to find a way to extract phosphates from the water and make fertilizer from it. And this will be expensive, but that's something that maybe we have to do. Okay? Something that we should be able to do is to learn to read this kind of analysis of soil. This here analyzes the soil, and then you have the organic matter, and we have there something saying that you have very high, or you have medium, or you have low. And in this case here, organic matter apparently is very high. Oh, this place receives proper composting. But the nitrogen is quite low. Maybe it's a good idea to do a crops rotation. So then the legumes like beans, soybeans, whatever, put nitrogen in the soil. Or maybe you need fertilizer. Okay? Phosphorus is apparently it's in the medium to high, so maybe this farmer here need to put some artificial fertilizer there as well. And you also have here potassium, magnesium, calcium, sodium, sulfur, many chemicals, but please learn how to read the amount of nitrogen and phosphorus in the soil. Maybe potassium, okay, because this makes the NPK. NPK is the classic nitrogen, phosphorus, potassium fertilizer. Okay, so learn how to read that. That will be quite important. Okay, very good. I just told you that we get nutrients when we do the farming. The farmer cuts the crop, sells to people, and then we eat, and then we defecate it. We make our feces that goes to the sewage. And the problem is that the sewage, sometimes it's treated, sometimes not very well treated, and it might end up in water bodies. And what happens if it goes to water bodies is that there will be a lot of nutrients for plants in water, especially some algae, to grow. And they love that bunch of nutrients. And they grow a lot, they grow exponentially. They make a massive amount of algae over there. And we think this should be good. But actually, is not that good because the growth is so fast, that they tend to block light, causing a big mortality of algae that cause a very big increase in the decomposers in water. And when the decomposers start eating everything there that was left over, they put the oxygen down. And when they put the oxygen down, the water bodies get a low oxygen level. This is called, let me see here, show you the name, BOD, biological oxygen demand. So basically, they consume all the oxygen, and the fish and the aquatic living there, they end up suffering, and that's a big problem. To illustrate that, we have here a graph. Don't worry much about the question here. We're going to be doing this question later. But this is showing us what happens close to a sewage, untreated sewage, that's thrown over here. Look what happened. Nitrate goes up, and then when the nitrate goes up, oxygen tends to go down, and suspended solids and other stuff. Okay, the algae love it, they grow, okay, but then you have bacteria and other stuff. So basically, it creates a havoc, it creates a big mortality. It's something for us to be aware, and this is called eutrophication. So eutrophication is this. It's a lot of chemicals, nutrients in water, create a biological oxygen demand, that makes the water to have less oxygen on it. Just because we're talking about food and composting stuff, I brought a curiosity here. This is an interesting infographic that shows 7 times technology almost destroyed the world, and 6 of them are nuclear. We got through 6 nuclear catastrophes that almost destroyed the world. And I'm not talking here about Chernobyl and Fukushima. Chernobyl and Fukushima were small. There were other 6, usually related to war, that were a big problem. But the point is that the one that's not nuclear was biological. And in 1992, scientists created a bacteria called Klebsiella planticola to be able to digest food waste and transform that into fuel. It was an attempt of scientists to use the leftover of food waste to make something useful, to make something renewable. Hey, that's good, that was great, and it did work. It was fantastic. However, just before they started making commercial use of that, after doing the tests in laboratory, there was a scientist that decided to test this in a real condition, throwing this bacteria, in the soil where there are plants. And what they realized is that that bacteria, genetically modified, ate all the leftover food, but also ate all the plants and everything. If this bacteria had been released, we would probably all be dead by now. So we got very close. It was just because one researcher decided, let's test this in a real life condition. And he realized that this bacteria would be eating all our plants. It would be Armageddon rating, 5 rates over here. It was the biggest threat that humanity suffered ever. So if you want to know more about that, QR code here for you. Here a little questionnaire for you to see if you nailed this topic on the nitrogen cycle and the phosphate cycle. See you in another lesson. Bye bye.